Good morning to all.
Good
Welcome to
morning.
day four. Welcome to day four of ASSHEE 2020. With your permission, let's start at first technical session of the day. Today we have Dr. Raghunath STG to deliver lecture on probabilistic seismic hazard map of India. Dr. Raghunath STG is currently working as Associate Professor in Department of Civil Engineering, IIT Madras. He was previously Senior Lecturer, Department of Civil Engineering, IIT Guwahati. His professional expertise are in the fields of natural hazards, risk assessment, wave propagation, structural dynamics, and earthquake engineering. Sir, I welcome you to ASHI 2020 technical session, and I request our convener, Dr. Seema Ghosh ma'am, to chair the session. Over to you, ma'am.
Thank you, Pooja. Sir, please, Rogan sir,
Thank
it's
you, madam.
over to you, sir.
Thank you, madam. Just share the screen. You are able to see, madam? You are able to
Yes,
see this?
yes, we
Thank you.
can see it. Yeah.
Okay. Thank you, Dr. Seema Ghosh. I thank, Dr. J.R. Kayal and NIT Agartala for inviting me to this workshop. So I think for the last 3 days, I have also been looking at these videos. Okay, in YouTube. I think we had wonderful lectures, covering all aspects of seismology, like hazard, then economic losses, receiver functions. I think earthquake clusters, 2011 Tohoku earthquake. So many interesting lectures was there, and today my lecture I will be focusing on the development of the PSHA map of India. And of course my lecture is little bit, my life is simple because the Russian professors, I think on day 2 they have already introduced you this subject of probabilistic seismic hazard analysis, where they discussed about IAEA guidelines, for the nuclear reactors. So the methodology is more or less the same, which we have adopted for our to develop our seismic hazard for our India. So now in our India, we have been using this seismic hazard map, which is quite old and which was developed just based on the past damages. It was not done as per, the probabilistic or deterministic analysis. So all the earthquake engineering experts working in the country said they felt that, this map has to be revised based on the probabilistic the principles. So there was a project in 2011, which was concluded in 2011 for about 3 years. So these are the committee of experts, like we have from geophysics, seismology, then geologists, then practicing engineers, geotechnical engineers, then insurance companies and others. So this report was brought out in 2011, and this project was given to us, and I was a the project investigator along with a CRC. So this report was brought out in 2011. So this is the existing seismic zone map. You can see on the my left side. So India has divided it into some 4 zones, which is and then they give the PGA levels, 0.1, 0.16, 0.24, and 0.36 G is the highest in the country. So now, so this map is based on the past damages only. And now this map, which is on the right hand side, is a PGA contours, which we developed in 2011 for using PSHA at 2,475 written period, and this is valid for A-type site. So although this map was accepted by the Bureau of Indian Standards, but there was some issues like we should be able to give it on B-type site, and then this Indo-Gangetic basin, how do we address this? And then there are so many issues were there from the practicing engineers point of view. So last year, once again, committee was formed, and then this project was awarded to us to develop this, to upgrade this seismic hazard map. So I will not go into all the past literature. So like before 2011, say all the literature review, like what are the important aspects in hazard and who has done all this work was documented in the India report, which is available, online. So now from 2011, if I see in the last 10 years, there has been a lot of advancements in India. The one is this Pesmo strong motion database. This was developed by IIT Roorkee. So we got lot of strong motion recordings in the last 10 years. Even the Nepal earthquake, that we have a new CIGN network in the Indo-Ganga basin. So this Nepal earthquake was also very well recorded, and its aftershocks itself. Then this ISC gem catalog came into picture. Then many papers have been published in the last 10 years by many agencies, by many professors, institutes, and independent researchers also are there. Then there are several reports have been released by nuclear agencies, ministries. GEM reports are there. Many consultancy reports are there, and there has been several GMPs, hazard maps, source zones, catalogs. Are available. In the last 10 years, there has been a huge advancement in this seismic hazard in India. So now to develop this hazard map for our the Indian building code, so this methodology was drafted by the committee of almost some 20 to 30 experts was there, comprising of geologists, then geophysics, then seismologists are there, then we have insurance companies, the practicing engineers, from private as well as governmental things, and many the professors are there. So the methodology was like, we have to do this hazard computation at 0.1 degree by 0.1 degree grid, almost a 10 kilometer by 10 kilometer grid in India. And then to estimate hazards, they say that minimum 500 kilometer has to be used to compute hazard at each sample point. Then when it comes to the earthquake catalog, so the committee felt that after reviewing all the several works, so magnitude greater than 4 can be taken as a threshold thing, and to compute these recurrence parameters. And to develop these catalogs, say IMD has their own historical catalog, then USGS, ISC GEM. Then there are several published papers are there on earthquake catalogs, and neighboring countries. Recently, our Nepal, Thailand, they also have done the seismic hazard maps itself. So they also have developed their own catalog. So all this information should be compiled to develop a catalog for our country, and which can be used for recurrence relations. Now for to do this catalog completeness, we know there are so many uncertainties are there. So one should use this steps method. Then that visual things has to be used. And then regarding maximum magnitude, this is a very, very tricky thing to estimate, because it's an extrapolation. So we have several methods are there, and we can get different values from variety of methods. So the committee, after doing a lot of review, so you can do those things also, but the observed max in each zone should be taken as observed value plus 0.5. And then to do this AB values, they said we should use this Kijiko's the recent papers, the statistical papers. And then there is also one more Wechert method, okay, which is more or less on the completeness thing. There's a little bit difference between these two approaches. So these two methods we should use to estimate this recurrence relations. And coming to the faults, the only those identified by official agencies like GSI, IMD, NGRI should be used in our analysis. And then there is recently Hima-Tibet map came into picture, which shows active faults in the Tibetan and Himalayan region. So these agencies faults should be used in calculating our hazard. And then previously we divided the whole our India into 32 broad seismic zones. So now a new source zone has been added in the Tibet region, because committee felt that earthquakes in that region also can cause some damaging ground motion in the Himalayas, that portion. So a new zone has been added. And then previously the old method was based on the faults, but the committee says that you have to do background seismicity models, because many countries are adopting, and there are a lot of papers on the background seismicity. So one is this elliptical smoothing, then circular smoothing, so these things have to be also should be used to compute the hazard maps. And so this is what the circular smoothing, so we count the number of earthquakes and then smoothen around a circle. Then this elliptical smoothing, so we combine the fault information with this background seismicity, and then using the fault's strike angle and the length and width, so we smoothen it around an ellipse around this faults itself. So this is just the methodology which is available internationally. So circular smoothing is a very popular thing, widely used in USGS and many countries. Then this elliptical smoothing is now becoming popular. So which combines both the circular smoothing as well as the fault. So we should get the results from all these approaches. And then coming to the GMPs, which we use in hazard analysis. Now in the older days, we don't have much data in India. So it was based on, the stochastic seismological models, even in Himalayas also. But now, as already I mentioned, in the last 10 years, we have Cosmos, PESMOS, then IMD data, then CIGN. a huge network, installed by NGRI group. So many data sets have come. So many people have published, this ground motion prediction equations based on the strong motion data. So the committee, our Indian building committee, felt that, our GMPs in Himalayas, IGP in Northeast India should be based on this strong motion data based. So, and then when it comes to peninsular India, central India, Gujarat, still our data is not complete. We don't have good quality, the complete data to establish these GMPs. So the committee felt that we can go ahead with the stochastic seismological models, or like in NGA East, say they are using these hybrid methods, like, you take data of active regions and then, use some correction factors and then come up with like this host to target, approach itself. So then committee also felt this, you should use multiple GMPs, the epistemic uncertainty. So you have to do a logic tree, and then, you should get for each branch, say you have to calculate all these numbers. So the methodology was framed by our the expert committee. So now using this methodology, say, so, we should get these results. So this is a fault map of India. I think tomorrow, I think Dr. Sujit Das Gupta, GSI, he is going to show you. So this is a fault map given by Geological, the Survey of India. So this, we have included the faults even in the Tibetan, this region itself. So just we broadly divided them into 30 broad, the source zones. So now coming to the seismicity, so all the historical events, everything has been documented in my previous NDMA report, and that earthquake catalog is available, online. Anybody can download that one. So now the committee felt that, we have to include the ISC JAMP because they have revised the epicenters and magnitude calculations. So to compare with those catalog also, then IMD has their own catalog, Indian Meteorological Department. Then USGS BRC, our atomic group, also runs some micro that earthquake surveys. They also give epicenters. And then NCS has come. Then Nepal, our neighboring countries. Then several papers and reports. So combining all these events and removing duplicates and others. So total around 68,000 earthquakes have been collected. For our entire this broad the rectangular region, to estimate our hazard analysis. So if we see the number of earthquakes which are greater than 8, it turns out to be some 26 events. So now, to decluster the things, previously in India, there are several techniques are there. We don't have any calibrations, like, how many aftershocks have to be removed, what should be the criteria. But now recent Nepal earthquake, it has all the aftershocks have been documented. So now we can do all these type of studies actually, like, Gardner-Knopf algorithm, Reisenberg algorithm, all algorithms we can test for this Nepal thing, and then we can calibrate these things for our earthquakes also. So based on this, we have developed, the declustering procedure as per this Gardner-Knopf Woodhammer's, this approach itself, and we removed all the aftershocks to estimate the recurrence relations. And completeness, as already I mentioned, the steps method, the visual methods have to be used. I am just showing for the All India catalog. So this has been done for all the individual source zones, at the local level also. So our catalog turns out to be something, it is complete for last, the 59 years, and for large magnitudes, some 200 years, the catalog shows the completeness. So this is how the temporal distribution. So the main historical earthquake is this, the one earthquake which occurred in Gujarat in 2000, some 500 BC itself. So we have collected all the historical things and we have merged with this instrumental data. So now this is also one more method, that is a visual screening. They say you have to plot the cumulative number of events and where the slope changes. That itself is taken as a completeness. So we estimate from all the approaches which are available in the literature. So then once the completeness has been done, now the recurrence becomes this one. So we estimated from Kijiko's method, where you come, the complete data, extreme data, you can incorporate all these completeness intervals and you can get these AB values and then this maximum magnitudes also. But as already I mentioned you, the Mmax, it is a very, very tricky thing. So to estimate Mmax, say, so we can estimate, there are several procedures are there because it is an extrapolation in statistics. Then we also did, the committee also suggested that, the Mmax should not be more than Mmax observed plus 0.5. So after doing all the studies, after discussion with, the NGRI and the Ministry of MOES and other scientists, so this has been arrived at the Mmax also. So now, as already I mentioned you, so we also do Kijiko's method is widely popular. Then there is one more Wechert method. So some people felt that the Kijiko's method, because it's very highly sensitive to the input starting values, so this also should be used in the calculation. So this method also we have obtained our recurrence relations. Now, so these are the for all the source zones, the p value, the lambda, then the maximum potential magnitude, and so we have reported here. And these are the old, the NDMA values in 2010, the old values, and these are the new values by including the recent, the 10 years data itself. Now, similarly, we have done from Kijiko's as well as from Wechert method, both the methods. There is a slight difference. In Kijiko's extreme things, we assume Gumbel distribution, but Wechert uses the same truncated exponential distribution. So these are the B values, we have obtained from both the approaches. And we have also obtained their uncertainties, like their standard deviations of the B value, then the lambdas, and its uncertainty also. So whichever source zone contains a very less data, obviously the standard deviation of B values will be very high. So then coming to the source models to do in hazard analysis. So there we followed three approaches. One is a fault-based approach, which was in the old report, this one. So the committee felt that, you should explore alternate things also. So we have done based on, as already mentioned, the seismicity-based approaches. One is circular smoothing, then elliptical smoothing. So we obtained hazard maps from all these approaches also. So this is a background seismicity model I am showing you using circular smoothened seismicity. So here you divide the whole region into some grids kind of a thing, and then you count the number of earthquakes, and then you smoothen it actually. Okay, so we have a correlation distance, So we have taken this as the 50 kilometers. So these are the contours obtained for circular smoothened seismicity. Now, similarly, we also did this elliptical smoothing because it combines, the seismicity with the faults itself. So here, instead of doing in a circle, so you have to do around the faults itself. So we have established all these things from the focal mechanism, solutions, and others. So we have given weightages for variety of the faultings, the thrust fault, strike slip faults, and other things also. And so these are the contours of the seismicity obtained from this elliptical smoothing. So now when it comes to GMPs, so the whole of our India is a very complex, geologically we have several things are there. So we divided the country into some, 3 or 4 zones, for estimating this GMP relations. So we have the Himalayas, then we have the Indo-Ganga basin, then we have central India, then we have peninsular India, then Kutch region, okay, so which behaves in a different fashion. So Gujarat we have, then of course northeast itself we have the subduction zones, then we have this Andaman region. So we divided this into several groups to for estimating our GMP relations. So now this is the data which is available in the last 10 years, and of course we had data previously also, but in the last 10 years there has been a significant the improvement. So you can see these blue ones are all the Indo-Ganga basin stations. Some of them were maintained by IIT Roorkee. Now NGRI is maintaining all these the stations in the Indo-Ganga basin. Then in Himalayas also NGRI has a network, even IIT Roorkee has a network here, and in northeast also there are several stations are available. So now using this data sets, we can develop GMPs also, or international GMPs which are of similar tectonic background we can take, and then we can even give a weightage, and we can do all the residuals, all other analysis itself. So this is how the magnitude distribution, it looks like the data, for our India, like Himalayas, IGP, then Northeast India. But when it comes to shield region, we don't have much data, only just some data sets like Gujarat earthquake, some far away broadband stations are there, then Koina, only few events are there. It is not that complete. So now using this data, so what we did was, because we have to do a logic tree kind of approach, multiple GMPs have to be used. So these GMPs should be come from a similar tectonic background. So I'm just showing here for the Himalayas and then this Indo-Ganga basin. So we have adopted like NGA West 2 equations here. So Atkinson, then Boers, Campbell's, and then these equations have been there. And then we have our own equations also. One has been developed by ID Gupta, Trifunax, one equation. Then we have my own equation which we developed from this data set itself. So we calculated all the residuals by comparing with the data, like log observed data minus log predicted value from the GMPs. And now, so this is for the Northeast India also. So we have taken some the equations from abroad, similar tectonic regions, and then we have done calculated all the residuals also. So like now to give find the weightages for all these equations, so there are several approaches are there: likelihood method, then log likelihood, Euclidean distance method. So we did all this type of the statistical analysis to find out weightages for this GMPs. And now we computed log likelihood, modified Euclidean distance. So I am showing you the references also. So by all the approaches we got all these numbers, and finally these are, I'm just showing you some comparisons, like how these international equations, when you want to try to compare with the data, say like Uttarkashi I'm showing here, then for the Nepal aftershocks and Nepal main events. So you can see for the Nepal main events, so this is a recorded data, it's a black line, and this is the one which has been developed by NGRI group, okay, which was published in BSSA. So international equations say, so here they are unable to predict, you said, far away distances itself. So like this, so we computed for variety of the conditions, and we did likelihood, residuals, and all those things we have done. And finally, you see, we computed like likelihood, then the ranking of this GMPs when you compare with the data, and then log likelihood and Euclidean distance. And recently there is a publication where they say, based on all the three, you should rank the GMPs, and we can find out the weights itself. So you can see in the Himalayan region set. So these are the weights, and this is a 0.242. So this is the equation which is locally developed with the data, that Gupta and Trifonak's equation, and this is our own equation is there 0.188. And similarly we have obtained all the weights for other international similar tectonic things. Now when it comes to IGP, say, so here also we have these weightages, 0.227291 we have obtained. The Northeast India also, so these are the equations, Jao, Kano, Youngs, and Atkins, and Bohr, so we have obtained the weights for all these GMPs. So this is our logic tree. So our logic tree, you see, we are doing from elliptical smoothing, we are doing from fault based, we are also doing from the circular smoothing, and then we are also have for each methodology, say, then we have recurrence parameters estimated from this Kijiko, then we have from Wichet's method, and then in each region, say, we have these GMPs, and these are the weightages. So like this, we did for Himalayas, then Indo-Ganga basin, then we have stable continental region, then we have for the subduction region also. Now, when it comes to stable continental regions, recently NGA East, that report released by, it was released in Peer Berkeley, that available online. So they have given some 17 GMPs. These are all, estimated from the stochastic seismological models. So this also we have used all the GMPs. Then we have our own, the hybrid method, as already I mentioned you, the Campbell's that host to target regions, the kind of correction factors we use. And then one more Atkinson Boot 2006, one more equation was there for the stable continental. So all these equations have been used with appropriate weightages. So these weightages have been estimated from our ranking of this GMPs. So now once we do GMPs, once we have the recurrence relations, once we have the background seismicity, all these things, so now we proceed to develop our hazard curves. So as already I mentioned you, so here we did with several methods: fault based, then circular, then elliptical, then there are kernel estimation method, what the zoneless method, which was also available, and GMPs. So we have a combination like strong motion data in Himalayas, IGP, then synthetic data in the central India, then we have the hybrid methods for peninsular India. So all combinations, you see, we tried. Now when it comes to the hazard methodologies, there are basically several approaches are there. One is the classical Cornell's, that the famous equation. Then one can also do from Monte Carlo simulation, like we generate synthetic catalogs, and then we can obtain here also. We can also get from physics based also. Now the mechanics is very well established, and we can use this split modeling techniques to also estimate this hazard curves. So right now we followed this Cornell methodology. We also got results from Monte Carlo simulation. Now this physics based things, it is still under it is under progress itself. So now I am just showing you the contour maps, for 475 years, 2475 years from fault based approaches. So fault based, if I use how that is a linear, we assume the sources as a linear sources. So what will be the PGAs? So you can see 475, 2500 years, say. So that is a 10% and 2% probability in 50 years. So fault based approach gives you, very low values when you compare with other things. Now, similarly, we do for PGA, then 0.2 seconds, long period, short period, at all the natural time periods, we have obtained these values. And this is now the background seismicity models using circular smoothing. Now, when you do the circular smoothing method, the thing what we observe is, the values are, extremely, they are on the higher side. So like in the Himalayas, we get, for 2500 here, 1.1 G, very high values comes into picture. The fault-based methods, they give very low values because maybe, the linear sources which we are using. And then when I do this, so we estimated from all the methods. So this is the contours for 0.2 second, that is a long period coefficient. So similarly, we have for short period, short period coefficient. Similarly, we have for long period coefficient also. So then, so then in our building committees, what they said was, this time in our code, we will give the values for 73 year, 475, 2475, 5000 years, and even for 10,000 years also. And we also should give you the median, then 84 percentile, then the 95 percentile also. Because now in our India, for tall buildings, many important tall buildings and power plants, people are trying to do this performance based seismic design. So if you want to do this performance based seismic design, say, you should have report, all these numbers. And even we should have this PGV, that's the P ground velocity, then the P ground displacement is a very important thing for serviceability checks in our structures itself. So all these things, we are going to report in our the new building code. So I'm showing you the elliptical smoothing. So now the committee felt that elliptical smoothing values, they lie in between circular smoothing and the fault based. It is something like, in between these two. So the committee, whatever, the consensus was, we will go ahead with this elliptical smoothing itself. So I'm showing you the 73-year written period. So these are 50 percentile maps. And similarly 475, 2475, so these values lies in between circular method and this, the fault based methods. So you can see in Himalayas, for 2475 is a 0.65, and if you come to Agartala, it is almost, 0.7 or 0.8, or that type of high values, are observed for 50 percentiles. And these are valid at B-type rock itself. So similarly, 5000 years, then 10,000 years. Obviously, 10,000 years will be extremely high. So this information is required for, the power plant important structures. 5000 years is widely used for LNG. Okay, the ASSHEE code, it recommends, you have to use this 5000 year written period also. And if somebody wants to do performance-based designs, all these numbers are required for a practicing engineer. So now these are the 95 percentile. Obviously, 95 percentile will be extremely high, because it is a mu plus 1.65 times sigma. So you can see the values are very high. So similar results are there, like 2475, 5000 years, then 10,000 years. We have this 95 percentile maps also. So now here the most important thing is, the Koina region in South India. So this is, it is like, we get high values in the peninsular India in this small zone. Other side is the values are on the lower side only. Now this is for 0.2 second, that is a short period coefficient. So similarly 475 to 475. So here also we have 50 percentile, we have 84 percentile, and then we also have this 95 percentile also. So this is for variety of written periods I'm showing. So now when we did this work, say, so the committee what felt was we have to report the uncertainty or the sensitivity of our parameters, like GMP weightages, say. So GMP weightage is also, just based on the data, and there are several methods, as I mentioned you, likelihood, log likelihood, Euclidean distance. So if I use a different method, I will get different type of numbers. Okay, so now how sensitive are our results for this GMP weightages? Then recurrence parameters, if I use altogether a different method or a different philosophy, how much these things will change. So we have done some sensitivity, this recurrence parameters also. Like if I change the weights, we have several results. I'm just showing you a typical, it's very small thing. So if I take equal weights, what happens? So what we found out was, the GMP weightages, our results, the second decimal is, some regions, you see, the second decimal in Himalayas and other region, they are sensitive only. But some places are there where even the first decimal, you will have a sensitivity. But this doesn't alter the numbers, that drastically, the weightages of the GMPs. Then similarly, so I'm showing for variety of written periods, we got these numbers. And then this is an important thing. If I use Kitchko's method, say, what numbers we get. If I use Wichet method, okay, what numbers we get. So here also there are some small differences are there, but not that drastic, or we don't see that much surprises, okay, in terms of the the PGAs at variety of written periods from these two methods. Some small change. There are some places where we get higher values if I use one method. If I use another method, say, we get some slightly, the lower value itself. And then so now in our India, say these hazard contours, 73 year, 475 year, 2475 year we can give. But our practicing engineers, they want, they are accustomed for our zones itself. So if I give a variety of these contour maps, it will be very difficult for them to understand. So what the committee felt was, we will go ahead with this zones itself. So what we did was, based on our hazard contours, say, so we divided the entire country into, you see, the 4 zones, like zone A, zone B, zone C, and zone D. So zone A means, the contours wherever the value is less than 0.15 G. So we are doing in zone A. Then zone B means 0.15 to 0.3 G, then 0.3 to zero point 0.6, then greater than 0.6 A. So we club them into zones, kind of a thing, because these things are very easy for a practicing engineer. Because in our India, most of the practicing engineers, say, so they are diploma or the BTech graduates, you see. So for them it will be very easy to use this the zone maps itself. So this is a zone map based on the 50 percentile hazard map, and this is a zone map, you see, based on the 95 percentile. So if you use 95 percentile, then zone D area will obviously increase. So now the PGA values for all these zones will be like, zone A is 0.15 G, then we have 0.3, then 0.6, and maybe some 0.84 G. So these numbers are under discussion, or the debate itself. Now we have also done like sensitivities, a lack of instrumental data. See, in India, what happens is, some places are widely instrumented. Like Koina region is highly instrumented. So 3 magnitude, 4 magnitudes, they report all this instrumental data. Now there are some regions like in Ganga Basin, or some places where instruments are not there. Earthquakes are occurring, the small quakes like 4.4 or 4.6, but they are not getting recorded there. So in hazard analysis, what happens is, wherever the instruments are high, the values are high, but wherever less instrumental data, say, the values are very low. So here also we did some kind of the sensitivity study. So like, if I delete from my catalog, say, all earthquakes more than 4.5, then what happens in the hazard? If I 5 magnitude, if I delete, what happens in the hazard? So that sensitivity studies also we have done, and we found out that in Bombay, some cities, if the lack of instrumental data, so we'll have the huge deviations at you see, the large return periods itself. So this is what I'm just showing, like Amritsar, if there is a lack of instrumental data, say, okay, so like, there are no earthquakes which are magnitude less than 5, so the hazard is 0.061. But if I include the small magnitudes, 0.177, so how these values are very sensitive also. So similarly, we have done sensitivity for the MX side also. If I let us say, if mistakenly, if I don't include one large magnitude earthquake, okay, how much will be the PGA variation? So how much these values are sensitive? So all these things we have done for in the new report. So now, another most important thing what came up in our IS code was this displacement response spectrum. Some of you may be knowing displacement based design, it is becoming popular now. So of course in the code we don't want to incorporate right now, but in maybe the future codes, say, so displacement method in a Euro code has this displacement response spectrum. So on this side also we have done this work, because we have a high quality data, the CIGN network. So we did some studies like fitting GMPs for the displacement response spectra, and we got even this uniform hazard, displacement response spectra for all the cities in our India also. So this is how the bilinear shape of the displacement response spectrum. So you have this TD where the slope changes from straight line. This is 2 straight lines. How this slopes, this TD varies in the country. So this is a contour map I'm just showing you here. So how this varies, like in Ganga Basin, say 8 seconds, 6 seconds, we get these type of numbers itself. And then now in India, so the main thing is hazard is one issue. All the hazard maps are valid at B type rock, that is 760 meter per second. But the most challenging thing in India is this Ganga Basin. So this Ganga Basin is a highly complicated geological structure, where you will see amplification not only from the soil amplification but the basin effects. So they become very, very important. So this VS30 type of amplifications, that doesn't work in Ganga Basin, because the depth of the sediments itself is something around 6 kilometers, 7 kilometers. Some places, when it comes to shield regions, say, it may be the lower side, but when it comes to Himalayas, we have this huge problem itself. So if you want to attempt this soil amplification, one has to include the basin effects as well as this nonlinear soil amplification also into our calculations. So in our codal committee also, they felt that VS30 doesn't work for our the Indo-Ganga basin. So the whole basin has to be modeled, and some numbers have to be taken up to estimate amplification due to this basin structure itself. Not only in Indo-Ganga basin, we have like Cambay basin, Kutch basin. There are several basins are there where you will see these type of basin effects apart from this ordinary one-dimensional, you see the soil amplification. So this also we have started working on this thing. So we have developed the whole basins in spectral finite element method we have started. So this is one the finite elements. Okay, so we have modeled the entire Ganga basin itself. So we have done piece by piece. So I'm just showing you one the cube along this the Delhi region. You can see the Kedarnath is here and the Mount Kailash is here. So this is a 3D finite element model which we developed to understand this basin effects. And you can see the basin also it goes like this. So as it goes towards the Himalayas, the depth of sediments they increase up to 6 kilometers or 7 kilometers, but when it comes to the shield region, you see the depth decreases. So this basin is a very peculiar basin. So based on all the receiver function analysis and all the other kind of studies, so we have developed a 3D the shear wave velocity models or depth wise the velocity model here, and the top shear wave velocity is around 475 meter per second. So this we have done for this one. So these are the the mesh, the spectral element mesh I am showing here. So these are the calibrated the broadband simulations we did, and we have done this matching frequency, the quality factors, the scattering coefficients, and all those things have been estimated. And we started, and this is also another the IGP mesh I showed you near the Delhi. So this is near the Lucknow Faizabad region in the Kathmandu is here. So to model this Nepal earthquake, so these are the finite element mesh I'm showing you. So I'm just showing you some sections and the shear wave velocity also varies inside this basin itself. So all those things by incorporating so we are able to compute this soil amplification and even the basin effects also, and even the effects of the Himalayan topography on the ground motion also. So these for the Nepal earthquake, we have validated all these computational models here. So these are Nepal earthquake. It was, as already I mentioned you, it was widely recorded in this Central Indo-Ganga network. So you can see these black ones are the recorded ones, and these are the simulated ones. So the long period waves are getting simulated in our this spectral finite element method itself. So this also I'm showing you from our spectrum simulations at Kathmandu station, which is very close to the epicenter. So here also we are able to reproduce the displacement forms and other things itself. So now we have even validated for several past earthquakes from PESMOS data, even from CIGN network itself. So there was one 5.4 event in 2011, 4.4 Himalayan events, as well as CIGN events. So we have simulated this broadband, low frequencies from SpecFEM, and the high frequencies is from the scattering Green's functions, and we combine them using that matching in the frequency domain. So, and these are the time history simulated and the recorded ones, and these are the Fourier amplitude spectra I'm showing here, and these are the response spectra. So these type of work we have calibrated with all several the past the complete data itself, and we have got very the interesting results, and we have tried to estimate this amplification in the Ganga basin. So this is a typical, we do this residual analysis. So recorded data versus simulated data. So to check whether there is any bias in our simulations for PGV, then PGA, then the spectral acceleration at 0.2 second, then 1 second, then at 10 seconds, So all those studies have been done, and the models have been calibrated by comparing with this recorded data. So then once everything calibration has been done, so we also tried, everybody says that in Himalayas, we have a central seismic gap, and Bilham's papers are there. Many geologists are also, geophysics are also speculating, you see a huge event is due in the central seismic gap of the Himalayas. So we have, these are hypothetical events. So we have tried to see how much this Ganga basin and the Himalayas, how they will respond if there is going to be such a great earthquake in here, because these studies are very important not only for the codal purposes like amplification and others. They are very important to compute this economic losses also. So these are the slips model. So we have our own slip model, the non-Gaussian slip model. We have developed a new model based on the past slips, and that paper is available in Journal of Seismology. So using our non-Gaussian slip model, so we simulated several synthetic slip feeds. So here, the correlation length, we have used variograms technique here. So the correlation lengths have been taken up based on the magnitude. Then the scaling relations are also, we have our own, we have developed the equations for that. So using, and then we model this as a truncated, the exponential distribution, the slip value. So then, so this is the slip I'm showing you some, we have generated some several slip values to understand, the effect of slip on the ground motion. And at each, so this has been divided into several subports. So at each subports, we have, a source time function we have given, and then we have computed the response of the all the stations in Ganga basin as well as in the Himalayas. So this is how the, this is the Himalayas here. So this is that central seismic gap, the rupture, the plane of the central seismic gap here. And the epicenter also we have varied, in both the directions, along the dip direction as along, you see, the strike direction. So this and these are our stations. Like we have put an array perpendicular to this fault, parallel to this fault, how the amplification, you see, looks like in Himalayas as well as in the IGP itself. So I am just showing you, some time histories like Chamoli, Tehri. So we have a dam at Tehri also. So how these time histories looks like Delhi, then Lucknow, Roorkee, Kashipur, at several stations. We have computed these numbers itself, and then these are the amplifications. Like at bedrock level also, I have a station. On the top of the surface also, I have a station. So the red one is a bedrock station, and the surface is the the amplification which we have got by by including the one-dimensional amplification, and then our the basin effects itself from our model. So you can see, so when the depth is very high, the amplifications are extremely high. But when the depth comes down, so like is it 0.6 kilometer at some places, we will see the amplifications are very less, and the main amplification is found out at the long period part of the spectrum itself. So now similarly, you see, we have done for a Himalayan event. Similarly, we have even done for an earthquake, hypothetical earthquake in IGP also, in the Indo-Ganga basin, that is near the Mahendranagar Dehradun fault, which has a magnitude of the 7.1, and then to see if earthquake occurs in Himalaya, how much will be the amplification. If an earthquake occurs beneath the Himalaya, how much will be the amplification. So our spectral finite element model was run, and here also we have generated some 30 samples of slip distribution using our non-Gaussian slip models. And finally, so these are the amplifications. What we understand is, the amplifications when earthquake occurs beneath the Ganga basin is entirely different when an earthquake occurs in Himalayas. So you will see different type of the amplifications. So some places will have de-amplification also, like if you see at 0.1 kilometer of the depth of the basin, so you can see there is a de-amplification in the the low natural period, but the long periods say we don't see any amplification here. And when the depth of the basin is very high, say like 4.6 kilometers, then you can see a huge amplification we see when an earthquake occurs beneath our Indo-Ganga basin. So now similarly, we have done for the IGP as well as the Ganga basin we have done. Now we have also looked at, you see, this Northeast India, because I was working in Gauhati for IIT Gauhati for 3 years. So at that time, we have done, we have developed several models based on stochastic seismological models. We have calibrated, and then we have done some simulations. So now what we have done is, here also we have a basin, that's a Brahmaputra. We have all kinds of topographical features are there. So how much will be the amplification due to this topography, then the basin effects, and then the soil amplification. So we have developed this finite element models, say, to simulate, you see, the ground motion even in northeastern region also. So this we have done a complete 3D shear wave velocity profile we have developed. So there has been many receiver functions. Yesterday I think we had a lecture. So using this receiver function analysis, many geophysicists, they report this one-dimensional the velocity models are there. So based on these models, and then based on the geology of the region, say, so we have interpolated them. We have done this the one-dimensional velocity models we have developed, and we have interpolated them, and we have got into some 3D full 3D velocity models we have done. And finally, this is a shear wave velocity model I'm showing you here. at the surface level. So Shillong Plateau, Migir Hills, say, because they have very high shear wave velocities. When you compare with Assam Valley, which is a typical basin, then Bengal basin, say, here also you have a huge basin type of a structure. So I'm showing you the VP variation, VS variation in 3D with the depth itself. So we have developed all these models even for the northeastern India. And then you see we have even validated, like from the geology, there are several sections have been shown. Okay, so how the shear wave velocity, you see the Indo-Burma subduction region. So we have compared with all these type of variations, several sections, and calibrated with geology as well as from the receiver function analysis. And finally, you see we developed this a 3D velocity model. It's a spectral finite element model, you see, for ground motion synthesis in northeastern India. So you can see this is our finite element model. You can see this is a zoomed version I'm showing you here. This is a finite element mesh, and you can see we have even modeled all the topography of the Shillong region, then Mikiri Hills, then Indo-Burmese Arc, as well as the Himalayan region, and we have assumed this 3D variation of material properties, and then we started simulating, you see, for all these earthquakes. So this is the details of the meshes. So how do we have digitized, how we have done our measure, and then the solver itself. So it is something 757.91 million degrees of freedom. So to run these type of meshes, you require a supercomputer. So our IIT Madras, you see, we have a supercomputer maintained by HP. So where we implemented all our that Ganga basin I showed you previously. So all those things have been implemented, and then we started simulating for the major earthquakes itself. So I'm just showing you some calibrations here. So we have not filtered the data. I'm just showing the recorded and the simulated time histories, say how they look like. So we are still calibrating our model itself. So like this, we have done for several all the past earthquakes. Several earthquakes are there in Northeast. So we are trying to calibrate our models with this one now, and I am showing you only the low frequency simulations, but we can do the high frequency simulations, and then we can combine them in a broadband, and we will compare with the data itself. So anyway, so with this, I will close my lecture so that we can have a discussion. So I just showed you, the proposal for a broad zoning of the country. So as already I mentioned you, the new seismic zone maps, which may come up in next 6 months or maybe 1 year. So several reviews have been done, like 4 or 5 times it has been reviewed. The methodology has been reviewed, and as already I mentioned you, this methodology has been drafted by the committee itself, and the report is also available online. The BIS has circulated to many groups for their comments and others, and whatever comments we are taking them, and then we are doing the sensitivity study also. So finally we will be having the hazard maps also, but as already I mentioned you, the practicing engineers of our country say, so they want to still go ahead with this zones itself, like 4 zones or 5 zones kind of a thing, and then give this value, because there are some practical difficulties. Like if in a city, say, if I give one street one value, another street another value, we will have a lot of the problems. So for that, this zone map has been prepared. So 4 zones, but these 4 zones have been estimated from the probabilistic seismic hazard contours itself. So as already I showed you, we have done based on fault based, circular smoothing, then elliptical smoothing, but everybody prefers elliptical smoothing, which combines the fault as well as this circular smoothing. So these 4 zones I have shown you, and these are the Z values. Like zone A will have PGA 0.15 G, then zone B the PGA may be something around 0.15 to 0.3. So this we are debating actually, okay, how much will be the values. And then because if I change the zones, the PGA values, automatically other codes also have to change. Our IS 456, the concrete code, then IS 800, the steel code. So many, because this map is going to affect all other codes for RCC and all other structures. So there are another committees are looking at, while if I take these values, how much will be the reduction, or how to select the R factor, how to select the I factor when I take these type of values, and then how to do. So those things are currently going on. So based on all those studies, maybe these Z values will be fixed up, but our Z value, the highest Z value will be something around this 0.8 G. That is what the committee also felt it is fine. Now right now we are having only 0.36 G, which underestimates the hazard at in Himalayas as well as in the northeast India. But if I increase the PGA to very high value, how it is going to affect the structure, or where R factor should be. So that is under people are working on, the Codal people are working on those issues itself. Then whatever zone map I showed you, that zone map is valid for B type site, that is 760 meter, that's BC boundary essentially, 760 meter per second. But how to compute the soil amplification? Right now in the code we give type 1, type 2, type 3 type of a soil, but and some groups prefer that VS30. Based on the VS30 you can classify and you can use it also, but VS30 doesn't work in our country, essentially in the Ganga basin, the river mouths, say, where depth of sediments are very high. For 6 kilometer in Calcutta, that basin you may have 10 kilometer the sediment depth. So VS30 is very poor. So what the committee says is, we should have a sediment depth versus amplification. So if I know n value, if I do, and if I know how much is the depth of sediments at my site, so we may give some type of a charts. Okay, so where depending on your sediment depths, you can choose your amplification also. So this work is under progress right now. So I will just close my thing with acknowledgements. As already I mentioned so this is a committee, not although I have done all the work, but all the inputs have come from these people like CVR. He is a chairman of CED 39, that is the criteria for earthquake resistant design. Then we have NGRI, Dr. Srinagesh and others also from NGRI. Then Ravi Sinha from Bombay. Then ID Gupta is an independent researcher and he does a lot of work in hazard analysis. Then DK Paul, who is a chairman of the MAPS subcommittee. Then we have Nuclear Atomic Energy Regulatory Board, Roshan, and then Professor Iyengar, who is my own supervisor, and then member secretary is there. And of course, NDMA has given our financial support. So thank you so much. Okay.
Thank you, sir, for your nice presentation. Audience, if there is any question.
Yes. In India, you have quite a lot of nuclear power plants installed. And
Yes.
for each of these NPP, specific engineering investigations have been done to assess the hazard level.
Okay.
Have you ever compared your map with these specific works? Are you getting more conservative values or compatible or less? Because you have made your calculations for the very lot of return periods, so you can have a good basis for comparison. Have you ever done that?
Yes. So as already I mentioned, right, our building code committee has people from nuclear, Atomic Energy Regulatory Board. So they have compared with their nuclear things like Bombay, Kakrapara, many nuclear reactors. I think you showed right on that day in your lecture. So that they have been compared, and our values are on the slightly on the higher side, to be honest.
Even higher than for the NPP?
Yes.
And another question. Your maps looks very mosaic. For 32 or 33 just source zones, this seems too much detailed. Is the really data supports this so mosaic output finally? Or this is just a matter of drawing isolines?
Followed. No, I agree with you. See, like as already I mentioned you, right, we have that 33, that because the data, if I decrease the size of the zones, the seismicity data will be very less. So AB values are highly sensitive, they fluctuate like anything. So B value, like Kijiko's method, you give some starting value, you will get something else. And if I change the data, something else will come. So based on the sensitivity, we adopted these broad zones. But as already I mentioned, we are doing background seismicity models also, where you don't require zones, just you divide it to grids and circular smoothing and elliptical smoothing, say. So we have from all the approaches.
Thank
and
you.
our building committee says is we should go ahead with the elliptical smoothing, which is because as a practicing engineer wants always less values only. So practicing engineers likes fault-based approaches, not based on this one, because they will give very less value, so they will be very happy to design. But circular smoothing, if you do, you will get very high values. Science is a different thing, but practicing engineers say no, you follow, right? It's difficult for us. So somewhere between this and this, we have elliptical smoothing. So it was agreed like elliptical smoothing may be fine.
Thank you.
Sir, there is another question from the participants. Is it seen on your screen?
Yes, yes. What kind of
Yeah.
nucleation method is used to replicate earthquake in your spectrum 3D model? So we model the earthquake as a displacement discontinuity, that slip model which I have showed you. So that is based on this random field modeling. So because we have done for a future earthquakes, the slip models are not known. So we model it as a Gaussian, non-Gaussian random field. It is a truncated exponential distribution, and it has its own power spectral density, which has a correlation lens, so which is scale with the magnitude. So we have used those models, to find out this in our spec fem, and then to get this type of result. Sir, what is meant by background seismicity? So background seismicity means you don't know the faults. See, there are many earthquakes in India. If I project on the fault map, you will see there are no faults there, but epicenters are there. So how do I handle these type of events itself? So what we try to do is, we remove all the faults. We divide the region into grids, like 0.1 degree by 0.1 degree kind of a thing. So we count how many number of earthquakes are there in each that small boxes, and then we do this smoothing by that expression, assuming a correlation distance, and we have uncertainty in the location of the source. So that is what we do as a background seismicity. The background seismicity means faults are not there. Only you would go just based on the earthquake catalogs itself. In the analysis of earthquake hazard, if you use artificial acceleration maps, does it give an acceptable result or not? I did not understand. Artificial means artificial acceleration means I don't understand. See, artificial acceleration, I think it means from the hazard analysis, whatever we are doing, because they are all from GMPs, so they have from the strong motion data they have been estimated. So as already, of course, does it give an acceptable result? I will just give answer in a different fashion. See, generally our design philosophy is, you can design for whatever value you like, but you should know your risk level. That is the most important thing. When I say 2,500 year return period, so the risk level is 2% in 50 years. So you cover the risk with insurance. Whatever value you take, there will be definitely some uncertainty. So that uncertainty you have to cover with insurance. That is what the building code, the philosophy is. Next one, could you please shed some light on whether period of completeness is strictly required to be done for each seismic zone for carrying out region-wise seismic hazard study? Yes, you have to do, it's a mandatory. See, if you do for the overall, you will get some result. If you do for the small regions, you will get some other result. But you have to report all the uncertainties, See how things are changing, you see. That uncertainty also may be included as in our logic tree. But yes, you have to do for each seismic source zone also. Yes, you have to do it.
Thank you, sir. Now, after completion of each session, from our organizing committee, our student members, they are organizing one quiz. So for that, I am handing over to Pooja. Pooja, please.
Yes, ma'am. Thank you, ma'am, for chairing the session. Sir, I request you to take up one question based on your lecture and give us to our participants so that they can drop their answers in the comment section.
Can I give now?
Sir, you can write also in the comment section, sir.
No, my question is very simple, ask them to define return period, that's all.
Okay.
That is very important for engineer, as far as I'm concerned.
So I give 1 minute time to our participants so that they can drop their answers in the comment section.
And maybe another question if you want, in international codes, what is the return period we use in design? In Indian code also, MCE they say, right? MCE earthquake, this one. So what is the return period for that? MCE, that's all.
So can you repeat the question once again, the second question?
So in our Indian code, IS 1893, we have a term known as MCE, okay? MCE. So MCE means, it corresponds to which return period? The first question is you define return period. The second question is in our Indian building code, MCA corresponds to which return period? That's all.
Okay. So let us give 1 minute time for our participants to drop the answers in the comment section. And we will choose the answer and we'll select the winners and we'll be announcing it in the next session or next day. And thank you so much, sir. We can conclude this session. Thank you so much for your informative session. I thank you once again, sir. And thank you, Seema ma'am, for chairing the session. And I'll be announcing the winners of yesterday's quiz. So I request Sultan to display the winners on the screen, please. Winners of yesterday's quiz are Tapas Roy, Ritik Pandey, Saurav Chaudhary, Ravi Shankar Vaishnav, Gautami, Abhishek Sharma. I also request the winners to send an email to ASSHEEworkshop19@gmail.com for further communication. Gautami, Abhishek Sharma. Congratulations to all the winners. And thank you once again. And thank you once again to everybody. Let's conclude this session, and we'll meet for the second technical session as per the scheduled timing. Thank you.
Thank you.
Thank you.
Thank you, Ravikant. Thank you so much.
Welcome back, everyone.
Hello.
Welcome back, everyone. Welcome to second technical session of the day. Is Mary sir, Zari sir connected? I am not able to see you, sir.
He was connected before, but I don't know now. Maybe he's put up the
Yes,
camera.
I'm there.
Oh,
Evidently.
yes.
Say,
Okay. Okay.
please turn on your camera, sir.
Do you have my voice?
Yes, we
Yeah,
can
your
hear
voice is audible, sir.
Okay.
Can you please turn on your camera?
I think Mehdi sir's webcam is having some technical issues.
Yeah, maybe.
The
So
camera
can
is
you
on.
just try once again?
The camera is on, but the pictures are not coming.
Okay.
But you can start the session.
Okay. Welcome to the second technical session of the day. We have Professor Mehdi Zare delivering lecture on the importance of seismic gaps and clusters in seismic hazard analysis. Professor Mehdi Zare is currently Professor of Engineering Seismology at International Institute of Earthquake Engineering and Seismology, IIEES, Iran. He is also Associate Member at Academy of Sciences, Iran, HDR University, Stansburg. He has been the Director of Seismology Research Center, IIEES, followed by IEES Vice President for Research and Technology. He has also been Director of National Center for Earthquake Prediction. I request Dr. J.R. Kyle, sir, to chair the session. Over to you, sir. Thank you.
Thank you, Pooja. It's my great pleasure to chair this session and to listen to our good friend, Professor Mehdi Jare, a famous seismologist on seismic hazard analysis. Globally, he is known, very well known. So, Professor Mehdi Jare, please start your deliberation. Thank you so much. It's pleasure to listen to you.
Thank you very much, Professor Kayal. Thank you, everybody. And hello, everybody, and those who are listening to me. I prefer to share the screen, and I ask you to make stop my camera because to have better connection, possible connection. Okay. Okay, do you have my PowerPoint screen actually?
No,
Not
sir,
yet.
it's not visible.
Maybe
Yeah,
yes.
yes, it is visible now.
Because I shared it, full screen.
Yes, it's visible. It's visible.
Is it shared?
Yes.
Yes, sir, it's shared. It's
Not
visible.
yet?
It is visible. Now you can proceed, Professor Jare.
This is visible? Okay. I start? Okay. I go.
Yes, sir, you
Yes,
can
please.
start.
I go ahead. Okay. Thank you to be among the lecturers of this prestigious international workshop on advanced seismology, seismic hazard, earthquake engineering, theory, simulation, and observations. And again, it is an honor for me to attend and to share some of the results that we have obtained in with my team with you. I want to emphasize on the importance of seismic gaps and clusters in seismic hazard analysis. As you know, there has been the cases that the seismic hazard analysis might be discussed. For instance, they are clearly fail to predict the actual ground motion. Uh, there are several examples, such as Amatrice earthquake in 2016, Italy, 2011 Tokyo earthquake, 2010 Haiti earthquake, 2008 Sichuan, China earthquake, and 2005 Balakut, Pakistan earthquake, and 1978 earthquake in Tabas in Iran. And there is a major question: is a seismic gap a major parameter to be included in seismic hazard analysis? The example of Toko 2011 9.1 earthquake is an important example because the probability of exceedance of such earthquake intensity was very, very low, estimated before the earthquake occurrence. It has been estimated in 2010 that it is a very low possibility for great earthquake. And a year after, the earthquake of Toko Sendai with the magnitude 9.1 has occurred. The deficiencies of seismic hazard analysis might have different sources because of seismic physical models, characteristic earthquakes and seismic gaps, or the points to be focused. The assumptions of activity rate, strain accumulation, release patterns of faults, and seismic clusters might be the sources of such bad assumptions. And the data that are incomplete, misinterpreted, and lack of data in order to be included for the seismic source zones. Okay, what are the seismic gaps and seismic clusters? The seismic gaps are a part of the fault for which we have the record of major earthquake in the past, but now it is quiet. There is in some seismic gaps there is no historical events, but it is believed that due to geological evidences on the fault, this fault segment is capable to produce earthquake, or it is a there is a major strain in the earth crust and plate motion, which shows that a major earthquake is possible. And what is a cluster? The clusters are either a group of foreshocks and aftershocks occurring before and after a big earthquake, and the other part are the big seismic events occurring normally in the plate boundaries, especially along the boundaries of oceanic crust. For instance, if you will look at the Mexico earthquake 1985, there have been a cluster before the 19 September 1985 earthquake of Michoacan, and there has been some other events before and after of this September 1985 earthquake, which has covered a part of Michoacan Gap, but there is still a gap in Guerrero part of the Apocho Trench border. Therefore, we may look as the major and minor earthquakes that occurred before 1985 earthquake as cluster patterns, as I have mentioned. And after the 1985 September 19 earthquake with the magnitude 7, there has been some earthquakes in September 21st and October 25, same year, that and thousands of smaller aftershocks. Therefore, we may speak about coverage of that Michoacan seismic gap because of these events, but there is still exists a Guerrero gap further toward the southeast of the Michoacan gap. Therefore, due to the strain that is building along this plate border region, we may think that there are some seismic gaps along this border plate boundary, especially where there is no earthquake, no major known earthquake. Other examples are the San Francisco Loma Prieta Parkfield seismic gaps. A part has been covered by October 17, 1989, Loma Prieta earthquake, but there are still some locked areas and the areas that strain, which are still building. And we may think about the other seismic gaps, such as San Francisco gap and Parkfield gap. And we know that the seismologist in California has estimated, we may say predicted, the Parkfield gap, that sometimes between 86 and 93, magnitude 6 or above may occur in Parkfield. But okay, never such earthquake has occurred, but magnitude 7.9 earthquake in Loma Prieta has occurred in 89. As I told you, in San Francisco and Parkfield, we may still think about a major possible earthquake to come. In Himalaya boundary, there has been 2015 Nepal earthquake, which has occurred in one of these gaps. There have been some pre-1900 and instrumental events after 1900 earthquakes that has covered some of these gaps before 2015 Nepal earthquake. But this part has been evidently covered by Nepal 2015 earthquake. Okay, what about Iran and Tehran. In Tehran, we have major faults, active faults, crossing nearby and we may say inside the mega city of Tehran, for which we have major historical and archeo earthquakes in the past, but recently we have no earthquake. Okay, maybe think about the seismic gaps along these faults. We may speak more about these earthquakes. Some other examples are seismic gaps in between 2009 and 2016, and the earthquakes of earthquake sequence of 2017 in Italy, in the Amatrice region in central Italy. Okay, and in Kuriil Trench in Japan. In Japan, we have the same situation, still toward the northeast of the Tohoku Sendai earthquake zone. We have some seismic gaps. Still, we think that the other possible earthquake may still come. Okay, I will focus a little bit more on the region of Middle East and Iran, for which I have more examples and more calculations to present to you. In Iran, we have something around 30 millimeter per year, shortening, and which is distributed about 22 millimeter per year in southern part in Zagros, and about 8 to 10 millimeter per year in northern part in Alborz region. And this is the cause, the major cause of the seismicity in this part of Alpine Himalayan zone. In 2017, we had some sequences. It has been started in November, and it has been continued by January 2018. In 12 November 2017, there have been Ezgele Sarpol-Zahab earthquake with a magnitude 7.3, and this earthquake of 2017 with magnitude 7.3 has occurred in the seismic gap region in western Zagros belt, in a region, in a part that almost nobody has expected a major 7.3 earthquake. Because it is the border of Zagros folded region, folded belt, and in this border, it is very rare to observe such major earthquakes. Okay. Therefore, if we look again at the possibility of such an earthquake, we may go through the catalogs and to the previous studies and look at the instrumental data. This is the broadband network of IIES, which is recording, and the short period stations of IRSC, Institute of Geophysics, which are recording the actual seismicity of the country. And this show a very general view of what we have as the source of our catalogs of seismicity. And if we focus on the 12 November 2017 earthquake magnitude. This is 2017, as I have mistyped 2020. With the magnitude 7.3, there has been as for the maximum displacement in Sarapol-Zahab region because of this earthquake. Aftershocks has been focused around the major faults toward its western part, and there and I have been focused on the type of faults, surface faults, and a possible basement fault, which might be observed based on the surface evidences in Sarapol-Zahab region. I do believe still that basement fault has been the cause of this 2017 earthquake. This is the model that I have proposed. I mean, after the November 2017 earthquake. As you see, the fault rupture has never reached to the surface because it was a rupture in the basement, crystalline basement of Zagros. It might be extended toward the folded crust, but it has never arrived to the sedimentary surface. And this was the reason that we couldn't observe any surface rupture in that region after the earthquake. I mean, surface rupture due to the earthquake fault. The rate of shortening in that collision area is about 6 to 9 millimeter per year, and it is very close to the Iran-Iraq border region. As you see, the Zagros mountain from fracture is very close to this region. The epicenter was between mountain from fracture and high Zagros fault, and this was the location of the epicenter. And as I told you, the surface displacement was evidently estimated. This is the GAFZ map. I mean, surface displacement has been calculated, and it has shown that it was a major uplift in the Sarapol-Zahab plain because of this earthquake. And this is the SAR interferometry data of that earthquake, and the displacement along Sarapol-Zahab fault. And these are some images of damage, I mean local damage in Sarapol-Zahab, and you see that about it was exactly 640 people died in that earthquake. In the same year, of 2017, we have been working on the earthquake clusters and sequences after the, based on the data in that region. But immediately after the 2017 earthquake, we have started to compile and to observe the seismic quiescence. Was there any seismic quiescence before the 2017 magnitude 7.3 earthquake? And we used RTL method. We have been Stefania Gentili and Antonella Perasan, and Dr. Talebi and myself and other colleagues. We have worked with people in Trieste and INGB Roma, and we published it in Physics of the Earth and Planetary Interior in 2019. We have observed that one of these, the earthquake of 2017 has occurred in one of these seismic quiescence areas, but we have observed that there is still three other zones for these quiescence. One along main Zagros main descent fault, and another one in eastern Tehran, which is very important in viewpoint of earthquake risk. I will explain more in this presentation. Okay, these are some surface displacement due to the landslide after the November 2017 Sarfar Zahab earthquake. But as I told you, we observed all the region, the epicentral region, and we couldn't find any evidence of earthquake surface fault rupture. It has been the landslide and landslide fissures, and there has been some tension cracks, but no surface fault rupture. As I told you, it was due to the depth of the basement fault. In the same year, about 1 month later, in eastern Iran, there has been 3 consecutive magnitude 6 earthquake in Kerman region, one after another. In 1st December 2017, it has been an earthquake with a magnitude 6, northern Kerman, western Lut area. This is the desert of Lut on the map, and this is the epicenter of that earthquake. In the 12th of December, there has been, and 13th of December, there has been 2 other earthquakes with magnitude 6, which occurred as a consecutive earthquakes, one after another, after the earthquake in, northern Kerman earthquake. Therefore, from 1st December up to 13th of December, we had 3 earthquakes occurred one after another as a domino play on the fault, the Kubanan fault in northern Kerman. And this shows the importance of seismic cluster in any possible seismic hazard analysis. A major problem in the country is the seismic risk of Tehran. We had in 20 December 2017, we had a magnitude 5 earthquake in western Tehran, about 40 kilometers west of Tehran. And in the 7th December this year, 7th of May this year, 2020, we had the earthquake in Damavand, again with the magnitude 5. Both of these events has shaken the city of Tehran. There are both moderate earthquakes, but you may think that about 20% of the population of the country are living in this region. Therefore, the impacts, I mean, social impacts of these two earthquakes has been very important, because a lot of people, both has occurred about midnight and made a panic, a great panic in the capital of the country. This is the view of the events occurred since 20th of December 2017 in around Tehran, in west of Tehran, toward in the Malard earthquake toward east of Tehran in Damavand in the 7th of May 2020. Very recently, one of the colleagues, one of our previous students, Mr. Momeni, has worked on the 2020 Damavand earthquake with magnitude 5. He has published an article with Professor Madariaga, and he has explained that this part of Mosha fault is under the impact of the activities of Damavand volcano. And it is very interesting that this part is based on the, I mean, the activities in magma chamber, in young magma chamber part of Damavand volcano, in the southern Damavand volcano. There is an increase of pore pressure on the fault, and therefore it caused decrease of normal stress on the fault, and therefore there are small to moderate earthquakes. And Dr. Momeni has explained that okay, even in on this segment we may expect a major earthquake of magnitude 7 or greater, and on the other segments, for instance, in a segment of Mosha fault passing exactly north of Tehran, this is the city of Tehran, we may expect an earthquake which has not occurred in at least in the last 1,000 years. Don't forget that geologically, this segment is an active segment, and it is very close to Tehran. Its nearest distance to the city is about 14 kilometers. What about the North Tehran fault? If we look at the North Tehran fault in the last 30,000 years, our colleagues have worked on this fault zone, and they have observed that there has been 9 earthquakes using the paleoseismologic investigations. They have found 9 earthquakes with a magnitude of something around 6 to 7.2, and 2 of the last events have been occurred in 7,000 years ago, which caused demolishing of a human civilization which existed in the region of capital. It has been certified by archaeologic investigation, recent archaeologic investigations in central Tehran region, actual central Tehran region, and another, I mean, the last, the real last earthquake, major earthquake, was in 3,200 years ago in in the northeast of Tehran, which demolished another, human settlement. And these two events is thought to be the earthquakes of magnitude 7. And after these events, there has been no earthquake, no major earthquake on North Tehran fault. Therefore, we may think about at least 5 seismic gaps around Tehran. One of them is located in northern part, and another one is southeast of the city. Okay, if you look at the historical earthquakes, historical means 300 BC up to 1900, and these are the earthquakes, recent earthquakes of 1970 up to 2018. The events show no major earthquake on northern Tehran fault, and this is a very important question. We may really think about that. Okay, if I want to show you the occurrence of historical earthquakes between 310 BC up to 2004. I may give you such order of occurrence of the events up to 2004, and you see that along the major faults in northern Tehran, there has been no earthquake in such window, time window. Therefore, this is the historical earthquake, means 2000, about 2,300 years ago. But if you remember, on North Tehran fault, the last event was obtained by archaeoseismology and paleoseismology, that occurred in 3,200 years ago. In 2000, before the 2017 earthquake, there has been a cluster in Western Tehran, and the aftershocks was again being represented to be a cluster. This is the western part of the city of Tehran, and the earthquake has occurred in Matash fault zone in southern Karaj, a city of 2 million inhabitants, is located in the hanging wall of this fault. And okay, if we look in Karaj, in the western Tehran faults, this is the location of that Malad earthquake of 20 December 2017, and this is the Coulomb stress change of that earthquake. There has been calculated 5 bars of increase in stress in both faults of eastern and western part of that event. Don't forget that the eastern fault segment is North Tehran fault, which is passing from northern parts of Tehran, and it is very important. Another evidence, geological evidence in that region, is the land subsidence due to water pumping in Tehran. The land subsidence has a record in that region, 35 centimeter per year. This is real. This is not millimeter. This is centimeter. 35 centimeter per year, and this is the average hydraulic head in between 1984 to 2012 in Western Tehran, and you see that the hydraulic head has, due to water pumping, has been increased, and this caused the major land subsidence in west and southwest of Tehran. If we uh, superimpose these land subsidence zone on the coulometric change of 20 December 2017 earthquake, we observed that the earthquake was occurred in the neighborhood of this land subsidence zone. Okay, about this change of stress about point 1 to 0.5 bar per year has occurred during about 30 years. We may think about 3 to 6 bars of stress change in about around 40 years in that region. And this instability of stress is occurred in the location that the North Tehran fault is might be triggered by the earthquake of, might be provoked by the earthquake of 2017 by 5 bars of stress increase. Therefore, the situation for this seismic gap, more than 3,000 years of seismic gap is complicated. And if we look at geomorphic levels on North Tehran fault, we have in that region, it is exactly the same region in Western Tehran. We have 3 geomorphic levels, 1350 meter, 1300 meter, 1250 meter. The vertical displacement on this seismic gap of North Tehran fault about 3 to 4 millimeter vertical uplift in last 100,000 years. And don't forget that this rate is occurred in a region that there has been no major earthquake in last 3,000 years. We have recalculated the change of probability for a magnitude 7 earthquake in North Tehran fault, difference of change of probability. The probability we observed fastly through the probabilistic, classical probabilistic seismic hazard maps for Tehran region for the return periods of 75, 475 years, and the levels of PGA, peak ground acceleration, are from 0.3, something around 0.3 to 0.65 G for the return periods of 75 to 2,475 years of based on our calculations. This is the vulnerability map for earthquake damage in central part and southern part of Tehran. We have more vulnerability. possible, and this is the population distribution. Most of the densely populated areas are focused in the same vulnerable areas in central and southern Tehran. We have made some scenarios for the earthquake. Two scenarios we worked. One was the same uh, part in northern fault with a possible magnitude 5, magnitude 6. You see that the blue line is the possible rupture we expect to produce such earthquake. And this is magnitude 7. You see that as far as the magnitude is growing up, the rupture length is increasing. It is normal. And we expect the magnitude for even a magnitude 7.7 want to occur, the rupture will be observed in the total segments of North Tehran fault zone. And if we look at the PGA assessment along uh, these scenarios, scenario 1 for a magnitude 5, this is magnitude 6, magnitude 7, third scenario, magnitude 7.7 in fourth scenario. You see that these are the deterministic assessments for the possibility of 4 different earthquake scenarios on this seismic gap. And this is the earthquake risk, possible earthquake risk for these 4 scenarios. And we made the same for southeast Tehran Evanaki fault with magnitude 5, magnitude 6. You see this blue line, which is growing up. Then we expect greater magnitude 7 and magnitude 7.7. This is the city of Tehran, and these are the seismic hazard levels. PGA assessment for magnitude 5, 6, 7, scenario 4, and 7.7. Scenario 3 is magnitude 7, and scenario 4 is magnitude 7.7. With them, with this deterministic assessment, and these are the risk levels based on these 4 scenarios. Therefore, you see that if we include the possibility of the earthquake occurrence on these seismic gaps, we may obtain the results as PGA level and earthquake risk level in different forms. And these are one of our assessment long-term probabilistic forecast of magnitude greater than 5 earthquakes in Iran. One of my previous students, Dr. Talebi, has been working in this published in Pure Applied Geophysics. And these are the map
Some network problem. The slides are not changed.
I guess sir is facing some technical issues. Let us wait for a few seconds. Sorry for the inconvenience, participants.
That's okay.
Sir is having some internet issues. Let us wait for a few more seconds. Please bear with us.
That's okay. That's okay.
So we'll be reconnecting in a few more seconds. So we'll be reconnecting shortly. We are really sorry for the inconvenience caused. Let us wait for a few more minutes. Kindly bear with us.
Sorry for speaking Russian. Робик, ну чё?
Я думаю, лучше не восстанавливать. Мгм. Я как раз тебе писал об этом. СМС-ку.
It is problem from our side or from Professor Jare's side? This
Sir,
problem.
he is having some technical issue with connecting to this.
Okay, Professor Jare, he is having problem. Okay.
Okay, guys. Okay, we'll take a short break and we'll come back soon. We'll be fixing up this technical issue and we'll be back soon. Thank you.
So we take a break for how much time? For 10 minutes,
We'll
5
take a break
minutes?
for 2 to 5 minutes and we will be back soon.
Okay, okay, that's fine.
Thank you.
So, okay, thank you.
Welcome back, everyone.
Hello.
Hello. Welcome back,
Hello,
everyone.
sir.
We regret the inconvenience caused. Sorry for that. And let us continue the session. Let's have question and answer session. Over to Kyle, sir. So you can take up the question for Zara, sir. So please unmute your mic.
So far from his lectures, it seems that from his model and lectures, it seems the Tehran earthquakes are depth range would be of the order of 15 to 30 kilometer, particularly in the interplate zone, or maybe less than that, less than 30 kilometer, maybe within 15 to 20 kilometer. But in the deeper zone, they are maybe some deep earthquakes, 30 to 50 kilometers. So I think these questions can be also, we can send to Professor Jare for the correct answer. But from his, from his lecture, and from his model, what I can get, he was talking about the Northern Tehran fault. I think he has come here. Yes.
Yeah, he has been connected now.
Yes.
Yeah.
Now
This is our
Professor Jare
question
has been
and
connected.
session now.
Yeah.
Thank you, Professor Kayal. I have seen the
Yes.
question. The average depth of the earthquakes in Tehran is something around 10 to 20 kilometers. And
Yeah.
therefore, there are shallow earthquakes, and therefore, we may think about a major if an earthquake occurs in Tehran, we may think about high intensity of the
Yes.
earthquake, of
Shallow.
any possible earthquake in Tehran.
Yeah. Any other
They are very
question?
shallow. Yeah.
Yeah. If there is any other question, Professor Jare is here to answer.
We can wait for a few more seconds for the questions.
Okay. And Professor Jare, do you want to conclude your lecture? We can give you few minutes.
Before concluding the session, let's take up one quiz question from Professor Zare sir for our participants.
No. I am asking Professor Jare whether he wants to conclude his lecture with one or two slides. If he wants to,
Okay.
then you can ask the question from the participants. So Professor Jare, do you want some? I think again he has gone offline or what?
I just show again this map. I want to share again the
Okay.
screen.
Okay.
Let's share the screen. The thing that I want, keeping in the mind the earthquake, probability
Yeah.
in the seismic gaps, and thinking about the short-term probability and long-term probability of the earthquakes with the magnitude greater than 5, there are observed some hazardous areas very close to the populated centers of the country, and meanwhile, the results that we obtain might be different, in some cases very different, with that classical assessment of seismic hazard for the return periods of, for instance, 475 years. And this is a major challenge today and in the future, in order to make more realistic seismic hazard analysis. It is evidently needs a need to have more complicated models. We need more data, and we need to work harder on such important zones. And this is a major challenge, not only in Iran, but in all hazardous parts of the world. For instance, in India, in Turkey, in Southern Europe, in Western United States, in Mexico, and in Peru, in Japan, in very, important seismic hazard zones of the world. This is a major challenge for probabilistic hazard assessments. Thank you.
Yes. So, should I? Yes. Yes, thank you, Professor Jare, for your wonderful lecture. We all enjoyed. Actually, you have shown how different gaps globally around the world and how dangerous there has been, particularly to Tohoku and other parts of the world. You have shown that the seismic, even in Iran, you have shown the seismic gaps areas, how risk they could be, and very nicely you have demonstrated us that northern Iran fault, how it could be dangerous, and you have simulated the acceleration for impending large earthquakes, which is not happening for last 3,000 years. So I think it was a very good message to all of us to be careful in the so-called seismic gap areas, and we should monitor seismicity, and we should do such type of seismic hazard studies. Thank you so much, Professor Jare. Now the questions are, the platform is open for the questions. Pooja, please, you can take up,
Yes.
please.
Thank you very much.
Thank you, sir. Thank you for the wonderful session. We all enjoyed it. Sir, I request you to take up one question from your lecture so that for a quiz session, so that the participants can drop the answers in the comment section. Sir, I request you to take up one question from your lecture for our participants for our quiz session.
I declare it right now.
Yes, sir. You can announce it. You can ask the question right now.
The question, that I can pose from my lecture in order to make a way to think more about the more realistic seismic hazard maps is what are the most important parameters in order to include seismic gaps in seismic hazard analysis.
Okay, sir. Thank you for the question. Sir, would you mind repeating the question for one more time? So would you mind repeating the question for one more time?
That what are the most important parameters in order to model the seismic gaps for seismic hazard analysis?
Okay, thank you, sir. Thank you for the question as well as
You
thank you
want
for
the answer?
No, sir. We'll take up the answer from you later on, so that we can give a time for the participants to drop the answers in the comment section. And thank you once again, sir, for the wonderful lecture. It was nice having you here. And thank you, Kyle, sir, for sharing the session.
Thank you so much. Thank you. Thank you, Professor Jare. Thank you so much. Wonderful, wonderful lecture. Vera, we all enjoyed your lecture. Hello. Hello.
Thank you very much for your kindness and hope for more collaboration.
Yes, yes, we hope. Thank you so much.
Thank you once again. Let us all meet again at 1:30 p.m. Thank you.
The ASSHEE international workshop was formulated in 2019 by NIT Agartala through an international collaboration with Russia, Finland, and Italy. It achieved an overwhelming success from the students, young scientists, engineers, and professionals, not only in Asiatic countries, Asian countries, and African countries like Nigeria, but also in developed countries like Russia, Finland, Italy, and Japan. The ASSHEE is now a phenomenal international platform to exchange knowledge, expertise, and experience for benefit to the society, particularly to the young students, researchers in the field of earth sciences, earthquake engineering, civil engineering, and seismic hazard mitigation. NIT Agartala reckons you to join ASSHEE 2020 for a wholesome experience in the field of advanced seismology, seismic hazards, and earthquake engineering. The
Hello everyone, welcome back. Coming to the last technical session of day 4 of ASSHEE 2020, we have Dr. Shantanu Barua delivering lecture on waveform modeling for fault plane solutions. Dr. Shantanu Barua is a senior scientist at Geoscience and Technology Division, GSTD of CSIR, NEIST, Jorat, Assam. He is also SSA membership by Seismological Society of America, USA for the year 2013. Complimentary 3 years AGU membership of American Geophysical Union through the Birken Grant Program from the year 2013 to 2016. I request Dr. Devajit Azarika sir to chair the session. Over to you, sir. Thank you.
Thank you, Pooja.
Thank you, sir.
I, on behalf of the organizing committee, I would like to welcome Dr. Shantanu Barua, Senior Scientist of NEIST Jorhat, to deliver his talk on waveform modeling for fault plane solutions. Dr. Shantanu is known to me since long time because we were from the same lab and we worked together. So he's a very well-known seismologist in the northeast part of India, and he's an experienced computational seismologist, particularly in the field of the seismotectonics and modeling of earthquake sources for source parameter studies. So Shantanu, I request you to kindly proceed for your talk.
Thank you very much. Am I audible?
Yes, sir, you're audible.
Yeah, thank you very much. First of all, I'd like to thank the organizing committee for giving me this opportunity to speak before you. And presently, I'm in a field work, so the internet connectivity may be sometimes maybe failure, maybe disturbed. So let me share the slides first. Is it coming?
No, sir, not yet.
You click on screen share.
Okay.
Share screen option.
Yeah. It has come now?
Yeah.
Yes,
It
sir.
come? Okay.
Yes.
Thank you very much. Okay. So respected dignitaries and the participant, today in this workshop, I'm going to speak on a topic titled waveform modeling for determining source mechanism of earthquakes. So I prepared a very basic slides because most of the participants are from students. The first, let us have a glimpse on the recent seismicity of northeast region of India. So these slides indicate the recent seismicity of northeast region of India from 1990 to 2019. The region has experienced two great earthquakes, one in 1897 in Ceylon and another one in 1950 in Indo-China border region in the year 1950. Besides this, the region also has experienced more than 30 large earthquakes in last 130 years. All these earthquakes have caused devastation to the region. And these are some photographs of devastation produced by 1897 great Ceylon earthquake. The first slide, the first figures is the Ceylon city before that earthquake, and this one is the city after that earthquake, and this is a famous police bazaar area before and after the earthquake. These are some more photographs of destruction due to that earthquake. And this is the photographs due to 1950 Great Assam earthquake destruction. So the important point is that at that time there is no availability of database, so the exact source parameters of these two great earthquakes was not known till yet. But for seismic hazard analysis, it is very important to know the source parameters each and every earthquakes. So in this presentation, I'd like to speak on the source parameters, how we can determine the source parameters using a very strong technique, which is known as waveform immersion or waveform modeling. So let me start. Whenever the subject seismology or earthquake come, the very first important observation for a seismologist or an earthquake engineer is to know about the physics of the earthquake source. Waveform modeling or inversion is such a tool which can easily describe the earthquake source in terms of some physical parameters which are known as source parameters. Now, what are the source parameters? Hypocenter, origin time, magnitude, faulting type, faulting size, seismic moment, stress drop, and source processes are some physical parameters. This is known as source parameters, and all these parameters are always associated with earthquake. One important aspect of source parameter is that the source parameter can also lead us in the evaluation of tectonic stress field and location of weak zone of a region, because earthquake occurs in a weak zone. There are three more parameters which are known as strike, deep, and rake. That all these three parameters can also be determined with the help of waveform inversion or waveform modeling techniques. So when earthquake occurs, the earthquake waves propagate through the medium and is recorded by a seismic station situated at the surface of the earth. Therefore, record of an earthquake, which is recorded by a station known as seismogram, carries information about the earthquake source as well as medium through which it propagates. Therefore, a seismogram contains the source effect, the propagation effect, and instrument response. Mathematically, equation or modeling are the two methods that can be used for extracting the information about the seismic sources and subsurface parameters from seismic data. Now, what's the basic difference between the waveform modeling and inversion? In inversion, the model parameters, that is the source parameters, are updated automatically until the residuals between the synthetic seismogram and the observed seismogram are minimized. In modeling, the model parameters are changed manually until a model is found such that the wave fields generated from the model can be best explained by the observed data. Waveform inversion and modeling are tightly coupled because inversion required numerical modeling and of wave propagation, and modeling needs a model that is obtained from the inversion. So, why we are interested for waveform inversion or modeling? Because with the help of waveform inversion, the associated fault or source of an earthquake can be characterized, which is the goal of a seismologist. So we know that when earthquake occurs, sudden rupture propagates along the fault, or earthquake impulse response is imparted to the surrounding through seismic waves, which create vibrations. In terms of physics, the earthquake source can be represented by a set of equivalent forces, but we all know that the equivalent forces cannot be quantified. Hence, we have to adopt the tensor concept. And thus, the force can be quantified from which the source parameter can be determined. Now, what is the equivalent forces? Equivalent forces are defined as the forces producing displacement at the Earth's surface that are identical to those from the axial forces of physical processes at the source. The equivalent forces are determined from the observed seismograms that contain information about the source and path and distortion due to recording. So, they can be represented by force couple that consist of two forces acting together. So, in this slide, I have shown a force couple, figure number A. Here you can see the first figure you can see it consists of a pair of forces acting in the direction of x-axis with a distance of d along y-axis, and this is known as mxy force couple. And the magnitude of this couple is F into d. F is the magnitude of the force, and d is the distance of the two forces. The other type of couple, that is mxy, shown in the right hand side cartoon, a vector couple dipole consists of forces offset in the direction of the force. Thus, mxs consists of forces of magnitude f acting in plus and minus x direction, separated by distance d. Here also, the magnitude of mxs is fd. The difference between these two force couple is that the first one, the left-hand side couple, exerts a net torque, while the second one exerts no torque. So, as a result of which, no geophysical processes have been found that can be modeled with single couples. On the other hand, if you can see the cartoon number B, it shows a different kind of couple, which is known as double couple, because two sets of opposite forces are acting simultaneously. One is mxy and another one is myx. As you know that the earthquake occurs due to slip, and in figure B, slip occurs in y direction. I have shown the slip direction in y direction. So it seems that the myx couple is intuitive because forces point in the slip direction. But we need to consider the mxy couple too for avoiding the net rock or the fault. As physics says, everything seems to be in the state of equilibrium condition. So the magnitude of the equivalent body forces is m naught, which is the scalar moment of the earthquake. Thus, if mxy and myx are couples of unit magnitude, the moment tensor can be determined by using a very simple formula, which is m is equal to m naught into mxy plus myx, where m naught is nothing but the seismic moment. So this slide shows a very simple double couple from which scalar seismic moment can be determined using a very simple formula, which is mu m naught is equal to mu ad, where mu is the rigidity, a is the area, and d is the displacement produced due to earthquake. So as we have three coordinate system, so moment tensor consists of 9 different double couples corresponding to x, y, z axis. The off-diagonal elements of the moment tensor are assigned to opposite forces that are offset in direction normal to their orientation and thus apply a net torque. But due to symmetry of moment tensor, the angular momentum is conserved, and hence we should have mxy is equal to myx. The diagonal elements correspond to force dipole acting along the coordinate axis. Thus, a moment tensor should have 6 independent elements, and it is symmetrical. Thus, if you know the arc structure and waveform data is available, the seismic moment tensor m and the focal mechanism of an earthquake can be calculated by moment tensor inversion. So this slide shows the physical representation of seismic moment tensor. So when earthquake occurs, what happens? The most fundamental observation is that material in the source region moves suddenly enough to radiate acoustic waves in all directions. Thus, the moment tensor is a convenient device, or it's a very convenient tool for describing how the amplitude of these seismic waves vary as they leave the source region. So this slide shows the different component of moment tensor m in x, y, z coordinate system. Jost and Herman in 1989 derived the component of moment tensor in terms of strike, deep, and rake in an isotropic medium for a double couple earthquake source. There is nothing in the physics of earthquake which requires that the source to be a double couple. For example, seismic waves will be produced if there is an implosion, as might occur in Earth if a phase transition occur or due to explosion of bomb, etc. In that case, we need to decompose the moment tensor, and to do so, we have to first consider the eigenvalues and eigenvectors of moment tensor m. So if mi is the eigenvalues corresponding to eigenvectors ai of moment tensor m, then we can write the moment tensor as shown in equation number 4, and different components can be derived as shown in equation number 5. So this slide shows how we can decompose a moment tensor. The sum of eigenvalues of the moment tensor describes the volume change in the source, which is known as isotropic component of the moment tensor. If the sum is positive, the isotropic component is due to explosion, and the source has impulsive component if the sum is negative. If the sum of the eigenvalues vanishes, then the moment tensor has only deviatory components. The deviating moment tensor represents a pure double couple source if one of the eigenvalues equals to 0. If none of the eigenvalues vanishes and the sum is still 0, the moment tensor can be decomposed into major or minor double couple or a double couple and a compensated linear vector dipole, which is known as CLVD. Arcing moment tensor with significantly large CLVD component have been observed in variety of tectonic environments, including Wadati-Benioff zone. Now, what is instrument response? To know the response of a seismometer, which can record the earthquake signals, we need to have the poles and zeros of the seismometer. The poles and zeros are the transfer function of a system. These values determine whether the system is stable and how well the system performs. This table, in this slide, the table shows the poles and zeros of different seismometers. And these values can be used to analyze the instrument response of the seismometers, which I'm going to show in the next slide. Yeah. So this slide shows the amplitude response, which is a ratio between the output amplitude to the input amplitude and derived from poles and zeros. It ascertains the passband frequency that is required for waveform processing or waveform modeling. And this is another response graph, which is known as phase response graph, which is a ratio between the output phase to the input, and is also derived from poles and zeros. The phase response of a seismometer is important because the recording of a seismogram is extremely sensitive to changes in phase. Now, what is green function? Named after British mathematician George Green, who first developed the concept in 1830s, green function enables solving inhomogeneous differential equation subject to specific initial condition. So in one words, green function is nothing but the earth impulse response due to an earthquake. Hence, green function gives the displacement at a point x resulting from unit force function applied at x naught, shown by this simple formula, which is shown as equation number 8. If d, small d, represents the observed displacement due to earthquake and ut represents the calculated one, then we must have dt is equal to ut. So in terms of vector, we can write it as d is equal to gm, where d is a vector representing the ground displacement, g is a matrix of green function, and m is nothing but the moment tensor element. So using this simple formula, d is equal to gm, we can invert our broadband seismograms to get the source parameters of that particular earthquake. Now, what's the methodology for waveform inversion? First, we have to take the earthquake signals, which having high signal to noise ratio and clear records of P and S level. Then we have to convert this signal into displacement waveform. Then displacement waveform are then low pass filtered below the contour frequency. Then we calculate the green function from the suitable cluster velocity model. And after that, we calculate the moment tensor. After calculating moment tensor, the synthetic seismogram can be obtained by multiplying the moment tensor with green function. So later, we matches the synthetic and observed seismogram, and if the matching is perfect, then we can get the required source parameters for that particular earthquake. I'm going to show some example of waveform inversion results. So this is an earthquake of 2003 recorded by 4 different stations: Tezpur, Rupa, Jogighopa, and Nagalbibra. So this is a waveform, and this is a pixel distance from the respective seismic stations. And this is a matching of seismogram. The blue curve indicate the observed seismogram, while the red one indicate the calculated or synthetic seismograms. And this is the ultimate result of waveform inversion, shown as a fishbowl, which gives the strike, deep rake, and seismic moment in terms of 9 centimeter. And from this seismic moment, we can calculate the moment magnitude of that particular earthquake. So we have derived the source parameters for some of the large earthquakes of northeast region of India. So this is an example of 18 September 2011 Sikkim earthquake. So this is a very large earthquake which caused around 111 people were dead due to this earthquake. And these are some photographs of destruction. And we have calculated, or we have estimated the focal mechanisms solutions for this earthquake. And we observed that the solution is a strike slip one. And for this work, we have used around 10 numbers of seismic stations. And from the observed or from the calculated waveform inversion results, we have derived a new tectonic model for Sikkim Himalaya region. According to our new tectonic model in Sikkim Himalaya, the earthquakes are due to a deep rooting strike slip fault and not due to any kind of over-thrusting or thrusting fault. And these are one more example of 2009 Bhutan earthquake. So this earthquake, as per our results said, this earthquake is nothing but a thrust faulting with strike slip component. But USGS has reported it to be a oblique kind of faulting. But we after using our own network data, we confirmed that the earthquake should be a thrust faulting with strike slip component earthquake. And as I mentioned, the focal mechanism can be used for determining the tectonic stress pattern. So we have derived the tectonic stress pattern for northeast region of India, including the Shillong and Mikiri Plateau, using the focal mechanism solution and source parameters. So here's an example. Here we can see in the figure, we have determined the stress pattern for Shillong and Mikiri Plateau. And for Shillong and Mikiri Plateau, we can see that the stress pattern of Shillong and Mikiri Plateau in the western side is oriented towards north of west, while in eastern part it is oriented towards north of east. And here I'd like to conclude my session, and I'll be happy to answer any questions from the student participants. Thank you. Hello. Hello.
Yes, sir.
Yeah.
So thank you for the wonderful session. We all enjoyed it. So let us come to the question and answer section. The questions will be displayed on the screen. Let us wait for a few seconds for the questions.
Dr. Deposit Hazarika, he's also very expert in waveform modeling technique. So he may also help me in answering any difficult questions. Yes.
We have questions coming up. Let's wait for a few seconds for the questions.
Yeah. I have to sort my presentation because I am in field, and the net strength is very slow. So I have to reduce my slides.
Yeah, that's okay, sir. Completely fine.
Yeah.
Okay, may I ask a question? May I?
I request.
Yes.
Okay.
Yes, sir.
First of all, thank you very much for the presentation. The question is that we heard that for the teleseismic distances, 30 to 90 degrees selected distances are most favorable because they have simpler path propagating. So they are not affected by the upper crust inhomogeneities. But as far as I see, you show the result which are obtained in the stations much closer to the source than 30 to 90 degree. How you deal with this complex structure of the upper crust? How much it can affect your result, these details of the wave propagation? Thank you.
Santanu is in line.
Yes, sir.
Hello, Santanu. Hello, Santanu.
I think he's been disconnected.
Okay, just can I interact or try to give
Yeah,
this answer?
sure, sir, you can take over.
Yeah. So usually what happens, we do not have a detailed crustal velocity model. Very fine structures, it is very difficult to get in a region. And if at all it is there, then also we cannot use these high frequency waveforms for modeling. So in such case, what we do in order to avoid these such complications, it is very difficult to consider that complexities in the waveform modeling procedure. So what we do, we take very low frequency. For example, 0.7 to 0.3 or 0. Maximum 5. Like that frequency band we select, so that we consider only the major effects, and we cannot consider the detailed effect because it creates again several complications while doing the modeling. So detailed crustal model, it is difficult. It has a limitation. We cannot do that. Only very low frequency, even for big magnitude earthquake also, very much low frequency is used for doing the modeling. So in that case, very detailed velocity we cannot consider in waveform modeling.
But in this case, if there were any comparison interesting with the global this CMT solutions, I mean, as far as you are using low frequencies, this means that more or less should be a good agreement with the CMT published result, just to understand how much they are compatible. Do you know any?
Yeah, sometimes in most cases for big magnitude earthquakes, we get good comparison between the CMT solutions and our solutions based on the local earthquake data. But sometimes we theoretically, it is better if we do with local earthquake data, because in global data, there very low frequency is utilized. So in our local earthquake data, if we have a good azimuthal coverage, then we prefer that the solution that we obtain from local earthquake data is much better. Yes, of course, for earthquake of magnitude 5 and above, more or less, it matches with the CMT solutions. And sometimes we get some discrepancies also. For example, in Bhutan earthquake, we get some discrepancies while doing our analysis. That small minor discrepancies will be there.
Because the local stations, they are more or less one-side stations, while the global has a better azimuthal coverage.
Yes, yes, sir.
Thank you.
Thank you, sir.
So we have one more question popping up on the screen. Why P waves are more dangerous?
Yeah, so P wave is not more dangerous. I will tell which wave is more dangerous. So P wave and S wave, they are body waves. They travel throughout the body of the Earth, and while they encounter the surface, then another kind of wave is produced on the surface. Then there are two kinds of surface waves are generated on the surface. One is a Rayleigh wave, which is elliptical Rayleigh wave, and other is log wave. Log wave motion is you can say in a layman language, motion of a snake, and Rayleigh wave is elliptical and retrograde. So these surface waves only creates a maximum destruction for man-made construction, bridges and houses. Not P wave exactly. P wave is yes, but P wave when encounters, then the surface waves are generated on the surface. So So that is much more destruction than, create much more destruction than you can say P wave is there, but surface waves are much more responsible for destructions.
One more question.
One more question. If we do not have surface features, how we will calculate seismic moment as we do not know the area? So in that case, because we in seismology, we do not go to the, every time we do not go to the field and measure the surface rupture area. So there are methods to compute the seismic moment, and there are empirical relations for computation. So seismologists, we wait only the waveforms recorded by different stations, and we adopt those empirical relations and mathematical computations to getting the seismic moment. Seismic moment is equal to mu AD. Mu is the rigidity modulus, A is the area, and B is the deceleerations. So those things can be indirectly, computationally, it can be computed without getting any field data. Next question is, we want to use first motion of a P wave to determine fault plane solution. Then how much distance seismographs we can use, because P wave attenuates with distance. Usually it is better if we get data within 500 kilometer epicentral distance, but more than that also can be used. But the main importance is not distance. Main important is azimuthal coverage. If we have good azimuthal coverage, then only we can separate, because the P wave fast motion is based on the compression and dilatation informations of the waveform. So if we have to have enough number of compression dilatation informations when we plot in stereo net, so that we can beautifully separate the compression and dilatation points. So number of stations are much more important in case of P wave fast motion polarity method. That limitations is not there in waveform modeling, because this theoretically it is different, and this is the basic technique that we used earlier.
Okay, so we can take up one last question. How does the sound you make travel in air? How does it travel in a cup telephone?
I could not understand. I think what is cup telephone is saying.
I request to make the participant the question very much clear, so that it would be much clear to understand and answer your question. Or else you can mail to our ASSHEE email ID, so that we can clarify you later at the later point of time. Okay, sir. Now let's take up a quiz question. As Shantanu sir is not able to connect, can you just, I request Devajit sir to take one question on behalf of Shantanu sir from his slide, sir.
Yeah. So another question again from Northeast, from Kyle sir's area, who is also very much interested. So we know in Northeast India, mostly several falls, lineaments, whatever, it is parallel or sub-parallel to the Himalayan arc. But there is orthogonal features that also is very much dangerous for, particularly for the Northeast India. Please name. My question is to name the fault that is orthogonal to the Himalayan arc in the Northeast India, particularly in Assam.
Thank you, sir. Sir, would you mind repeating the question for one more time?
I'll repeat one more.
Sure.
What is the orthogonal fault? What is a fault in the India that is orthogonal to the Himalaya, and it is very much active? And
okay,
and another thing, what is the type of fault? Whether it is thrust, normal, or strike slip.
That is in Northeast India or in the whole Himalaya? In Northeast India.
Northeast India, I'm telling, sir.
Yeah. Okay.
I think question is clear.
Yes, sir, it's clear. And thank you for the question, and thank you so much for chairing the session as well. And I even thank Shantanu sir for the wonderful lecture. Thank you once again. We can conclude today's session of ASSHEE 2020. Thank you everyone for your patience, and I thank all the participants for their patience as well. Thank you once again.
And for my side also, for my side also, I would like to thank you, Santanu, for giving this
Thank you,
significant lecture.
Ruben.
Thank you so much.
Thank you once again. See you all tomorrow at 10 a.m. IST. Thank you. Have a good day.
Okay. Okay. Thank you so much.
So for tomorrow, just a small information for the company. For tomorrow, I can participate only the morning, early morning session, because then I have to attend the scientific council sessions. So then suddenly tomorrow I will leave, and Vera too. We have to participate. Our internal and very important for us meeting. So
But
just
how
in
about,
case, huh?
How about validated at 3 p.m.? I think your presence is necessary. Validated session.
We will see. Anyway, I will just tell a couple of minutes before. Maybe I will ask Flor to say thanks before leaving. But anyway, I must be at this scientific council.
Okay.
So, okay, thank you.
Okay, sir. Thank you.
Bye.